Hey class, welcome to chapter 19 of organic chemistry. I apologize for not getting this out a little bit earlier. I'm trying to figure out how to get everything integrated to YouTube and make sure y'all get a good learning experience this week or maybe in upcoming weeks depending on what administration decides regarding our classes. But in the meantime, I will make the best of a tough situation and go on. So feel free to always email me if you have any questions regarding this. I'm going to give you this chapter in segments so that you don't get overwhelmed by one really long video, but I'll try to divvy it up, and by the end of the week you'll have the full week's worth of material that I was to lecture on anyways. And so what you're going to see is this should come in the YouTube video, and you're going to see me draw on the screen and lecture just as if we were actually in class. So here we go. Chapter 19, Addition, Substitution Reactions of Aldehydes and Ketones, Carbohydrate Chemistry. And this is a popular chapter for students. So here's some of our learning objectives. First, we're going to examine hemiacetals and acetals in a more detailed way. So recall before spring break, we talked about these functional groups, hemiacetals and acetals. We showed how to form them along with geminal diols and cyanohydrins and structures of those types, which ultimately centered around reactions with carbonyl groups. We're going to learn what it means to protect aldehydes, ketones, and alcohols using acetal functionalities, and then to subsequently deprotect them in use for synthesis. We're going to apply these concepts towards synthesis of more complex molecules using reactions we're used to. And then we're going to represent carbohydrates in a number of ways. And then this is going to be pertinent information as we delve into biochemistry later on in your academic journey. So here's our chapter theme: for every house is built by someone, but God is the builder of everything. Hebrews 3 verse 4. This is a good theme for this chapter because carbohydrates are one of the four main classes of biomolecules. And so what we're going to learn about is functional groups and reactions that really show themselves to be a central reaction in terms of biochemistry and the foundation of life here on this planet. All right, so here comes acetals and hemiacetals. So in chapter 18, we learned about addition reactions to carbonyl groups. And such reactions might have been gem-diol formation, cyanohydrin formation, acetal and hemiacetal formation. But we also saw this in chapter 15, right, when we examined Grignard reactions and organocuprate chemistry. And we also saw it with organolithium chemistry. Of course, organocuprates did not directly react with the carbonyl group, but could do 1,4 conjugate addition, if you recall. In the next two chapters, 19 and 20, we will elaborate on the utility of these reactions, yielding either substitution products or elimination products. So what we have going on here is a carbonyl group, and recall that it kind of had a partial positive right here and a partial negative on the oxygen due to the electronegativity or the dipole moment. And we're going to show you, I'm going to change the color for this. If we were to react it with a nucleophile with an H, and from chapter 18 we discovered that such a reaction would give you a nucleophile attached here and an OH, right? And now what we're going to do is we're going to continue on and show you what's going to happen in the next couple chapters. And what you're going to see is that in chapter 19, this is going to be the substitution version. And in chapter 20, we're going to show how elimination occurs. And the products of such reactions are shown right here. So you might see a nucleophile. And remember, substitution, you would then have an X right here. So you're replacing the OH group with an X. Okay? And then in chapter 20, remember with elimination, you always form a double bond of some sort. So what you're going to see in this chapter is your nucleophile here. But this time you have a double bond, so some form of elimination occurred. And or what you might actually see is a double bond to your nucleophile, depending on what's going on. So these are the types of reactions we're going to be examining in the upcoming chapters. But here we are in chapter 19, and this is going to be pertinent to alcohol and ketone and aldehyde protection and deprotection, and also carbohydrate chemistry. Okay, so here's an overview. We've already discussed most of these matters in the previous chapter before spring break, but if you remember acetal protection, or sorry, hemiacetal formation in the acid catalyzed manner, you would have this oxygen, and I'm going to switch to a laser pointer view. This particular carbonyl group would reach out and grab a proton from the acid, in this case sulfuric acid, thus protonating the oxygen, giving you the oxonium ion or oxonium cation, which is in resonance form. You see that's resonance arrow with a stabilized carbocation intermediate. Now, in the previous chapter when I discussed these matters, I had mentioned that we would actually take that structure and use it. I failed to mention that the carbocation version of this is technically the more stable one because carbon is less electronegative. Okay, remember oxygen is electronegative, thus it wants a negative charge. So placing a positive charge on an oxygen isn't necessarily the worst thing in the world, but if you can form a resonance structure where the positive is on the carbon, which is less electronegative, that is considered to be the better structure. Okay. Moving on, we could do a nucleophilic attack. In this case, we are using methanol or an alcohol to do a nucleophilic attack. So there it goes. It attacks the carbocation. Now keep in mind, we could have used the previous resonance structure to accomplish this by going here and then that there. Okay, I can actually demonstrate that using the pen in case you wanted to see what that looks like. That's probably the transformation you're more familiar with seeing. Okay, now moving on, you would then form, it almost looks like a hemiacetal, right? You have a central carbon here indicated by the laser pointer, an OH bonded to one side and an OR bound to the other. Except for we just got to deprotonate that to finish off the mechanism, which is this last step right here. And so your conjugate base of the sulfuric acid is going to deprotonate, thus yielding the hemiacetal product. Recall it has a central carbon bound to two oxygens. The hemiacetal, one of the oxygens is an OH, or hydroxyl group, the other is an ether. And recall that you reform sulfuric acid, which is needed to start the process off, so it is thus a catalyst. One thing I want to quickly point out is that this is an unstable product. Now, they're normally unstable, I should clarify, because what we're going to find out in the next slide is that cyclic hemiacetals tend to be stable, but acyclic versions are unstable. So we're going to take a look at the chemistry involved in these processes. As noted on the previous slide, hemiacetals and geminal are typically unstable. Okay, they're unstable. And the equilibrium actually favors the reactants over the products. And you say, Dr. Morris, why'd you teach us this in the first place if it's not even going to form the products that you told me? Well, I'm going to show you a little bit more detail behind the reaction and how you can actually get it to work. Okay, and so this is going to delve back into general chemistry as we discuss matters such as Le Chatelier's principle and whatnot. But there is one exception. I mentioned this in the previous slide, and that's that if you form cyclic hemiacetals, they tend to be stable, but only if you form a 5 or a 6-membered ring. Okay, so an example of this might be you take this particular aldehyde, and let's say it has however many CH2s attached to it, and then you have a CH2 bound to an OH. Okay, the equilibrium, actually whenever you're forming a cyclic hemiacetal in an acid catalyzed manner, would actually work out okay. And then this O would have formed that new bond, okay, which drawn looks like a 4-membered ring, but keep in mind what this N means right here, it means it could have been any number, and so typically these are favored whenever that number is such that would yield a 5 or 6-membered ring. Okay, so in our case it would be 2 or 3. Now, as I said, this forms most readily when a 5 or 6 membered ring can be generated. We're not going to talk about why that is the case, but as we saw in previous chapters in OChem 1, 5 and 6 membered rings tend to be pretty stable due to the bond angles, torsional strain, dihedral angles, and 1,3 diaxial interactions and whatnot. So 4 and 7, they don't make the cut. Okay. Let's take a deeper look at hemiacetal structure and why these processes are in equilibrium and why we might need to use Le Chatelier's principle to get what we need to out of these. So hemiacetals have 2 sites that can react with acid. You may have noticed, maybe you haven't, and that's fine, that whenever there's acid present, this O that I'm circling could also be protonated, okay? And that was A, and B can also be protonated as well. They're both oxygens with 2 lone pairs on them. Either can reach out and grab an acid. And so you may presume that that could have grabbed that H, or if there was an H here, that could have grabbed it. So the question is, what's the consequence if A would have done the grabbing, okay? Well, if you look at this statement right here, if A is protonated, as indicated right here, then you'll simply go back to the starting materials, which in this case would have been methanol and cyclohexanone. Okay, so do you see, if I erase some of this, do you see that if you would have protonated that, it would have yielded a molecule that looks like this? Okay, now all it has to happen is that has to drop its electrons down. Sorry, I drew that wrong. Drew it in the wrong spot, didn't I? Okay, all it has to do is drop those electrons down right there, and then you can kick off methanol to yield that oxonium plus CH3OH. And you know that that oxonium right here can easily be deprotonated to yield the cyclohexanone again. So what I'm trying to show you here is that that process, reprotonating A, is not very useful. Okay, it's not very useful. You're just going to go back to your starting materials, which happens quite often unless you manipulate the equilibrium to favor the products as you hope to. But notice that if B is protonated, you can actually lose water to form a resonance stabilized cationic intermediate. So that's what's shown down here. You have that same structure indicated in the bullet point above. And this time you're using B to do the protonation. And so it gets protonated by sulfuric acid, yielding OH2+. Recall that that's nothing more than a good leaving group, and that leaving group would be water. Okay, so what happens is, if you follow this mechanism right here, the lone pair from the S ether would come down and boot off the H2O, which is a favorable process. It's called a dehydration, and which you'd form is this oxonium cation, which has a resonance stabilized intermediate. Now, what's important about these structures indicated here, let me get the laser pointer, indicated here, is that they are susceptible to nucleophilic attack, right? You know where the laser pointer is indicated, a nucleophile does not mind attacking at that point, or if the resonance stabilized intermediate. You can also attack that carbocation. They're equivalent structures. You know, one's maybe a little bit more favored than the other, but they both represent essentially the same thing. And the thing that's being pointed out is that right here at this carbon, it's susceptible to nucleophilic attack, just like we've seen in other carbonyl chemistry. Okay, so key takeaways from this slide is that in a hemiacetal, there's 2 sites of protonation. One would be the ether, in which you just go through unproductive, an unproductive pathway where you regenerate starting materials. Or if you were to take the hydroxyl group in B and protonate it, you can actually lose water and then do further chemistry, okay? And that's where we get acetal formation from the previous intermediate. So the resonance stabilized cationic intermediate from the previous slide is susceptible to another nucleophilic attack from excess alcohol, which can form the acetal. This is not new news to you guys, as we discussed this already in chapter 18 in acetal formation. You may recall that it was the quote long mechanism that y'all didn't like very much. All what I'm doing is I'm showing you that mechanism, but this time showing you a deeper look into it. Okay, so if you were to take the intermediate from the previous slide, it looks like this with a carbocation right there. And I mentioned that this is done with excess methanol, CH3OH, with your lone pairs right there. Now, obviously what's going to happen is the lone pairs from the methanol are going to act like a nucleophile and attack right there at that carbocation position. And the result of this transformation is going to be this substituted cyclohexane. Okay, with a positive charge on it. Now you have your conjugate base of the sulfuric acid, HSO4 minus. That's just going to deprotonate to reform your sulfuric acid. And you may notice, voila, you just formed your acetal product. And you reformed your sulfuric acid, which is your catalyst to begin the mechanism once again. And so hopefully you can notice that this is an acetal, and that this carbon that I'm bulleting right there has two O's attached to it, and both of those O's are an OR group. Okay, so the hemiacetal group is a very special functional group that's in equilibrium and can reform starting materials if you protonate the wrong group attached to the carbon bearing the hemiacetal. But if you undergo protonation on the correct carbon, you can actually force it to an acetal product. Now, I just used the word force. I'm going to show you what I mean by that. So here's how you use equilibrium to your advantage. Since the reaction is in equilibrium as described in the previous slides, one needs to be clever in order to get a high yield of the acetal product. So it just doesn't magically happen. We have to use our skills and what we know about chemistry to favor the product side. One way you can do that is by distilling off water. This is the same distillation technique used in lab with that distillation setup, fractional or simple distillation. And the idea is that you're bubbling your reaction, you're stirring it around in that pot while heating it, and you heat it enough to where water starts leaving the reaction, thus driving the reaction towards the products. Okay, you may recall from general chemistry, this is a principle called Le Chatelier's principle. And that's all what you're doing. You're using the principle discovered by Le Chatelier to your advantage, even in organic chemistry. So look down at this slide, and you'll see here's your aldehyde or ketone. And then you mix it with excess alcohol, ROH, and TSOH. TSOH is toluene sulfonic acid, indicated right here. You see the toluene and you see the sulfonic acid group, SO3H. In fact, I bet you can think of a way to synthesize that molecule using the chemistry from chapter 17 about benzene. But anyways, it's just an acid. Think of it that way. It just tends to be soluble in organic solvents. Well, of course, you form the hemiacetal intermediate, but recall what I said a few slides ago. It's in equilibrium, yes, but it favors the reactants, which is why you see the equilibrium arrows favoring back this direction. All what that means is that it favors protonation of the OR group over the OH, because in order to form the acetal, recall that you had to protonate the OH to get this to work. But you may notice that if you have more ROH in toluene sulfonic acid, this equilibrium is actually equal. It's not favoring one side or another, but looky here, you end up forming water as a product. Now the question is what if you remove that water in a clever way, such as distilling it off? It's going to continue making equilibrium favor that direction. Okay, there it goes, to the right, because it's trying to balance itself out. And if you need help with Le Chatelier's principle, go back to your OpenStax general chemistry textbook and find Le Chatelier's principle. It's one of those chapters in that book, or you can just look at a YouTube video. But there's various ways you can use Le Chatelier's principle to your advantage, such as increasing the temperature or using pressure, or in this case, manipulating the amount of products or reactants formed. Okay, in this case, we are getting rid of water, thus shoving the equilibrium that direction. Okay, and it keeps on pushing that way to favor the acetal product. Another way is there's drying agents such as calcium chloride you've used in lab, magnesium sulfate, sodium sulfate. We've used something called molecular sieves. Those particular reagents, they absorb water, so they do the same thing as distilling it off. Okay. Again, this can seem very confusing, especially because we're not performing this lecture face-to-face. So feel free to email me if you have any questions. You do not need to memorize the structure of toluene sulfonic acid, but I do want you to know that it is a strong acid of equal strength to sulfuric acid, but they tend to use it, TSOH is the abbreviation, because it's soluble in organic solvents. So here's what I want you to work at home on your own time. Benzaldehyde, y'all know this structure now from what I made you memorize in chapter 17. Recall that CHO is the same thing as an aldehyde. And what it's saying is you react it with, this is called ethylene glycol. Here's what it looks like. And you end up forming this acetal. Do you see that it's an acetal? I bulleted the carbon. It's bound to two OR groups. It's a cyclic OR group, but it's still an acetal nonetheless. Try to draw this mechanism on your own time using the steps shown in the previous slides. Recall that this is an equilibrium, and that you would reform TSOH. And let's also assume that you're distilling off water or getting rid of it in some way to favor the product side of this reaction. Now, sometimes you want to go in the reverse direction, meaning you want to go from an acetal back down to your hemiacetal structure and then all the way back down to your original aldehyde or ketone. Well, here's how you do it. It's simply the reverse of the forward mechanism you did in the previous slide. Okay, so as you went from an aldehyde or ketone all the way to the acetal, just go in the exact reverse direction, step by step, to get you back to the original starting materials. Okay, this is going to be important when we talk about protection and deprotection in this chapter. But simply put, you may notice that right here is an acetal, and then you just protonate it using an acid. That could be toluene sulfonic acid, TSOH, or H2SO4. And then what would happen is you would end up kicking off the protonated oxygen species, which is just going to leave us methanol. It's just going to leave us methanol. And then you get this oxonium intermediate, knowing that that carbon that I just bulleted is susceptible to attack as shown by this resonance structure. And so that is susceptible to nucleophilic attack. Well, in this case, you're going to use excess water, okay? In the forward direction, meaning in order to form the acetal, you're going to use some acid, a catalytic amount, and a whole lot of alcohol to favor the product side. In this case, you don't want any alcohol in the mix, and you want a lot of water because you're trying to go in the reverse direction. So notice in this case, water comes in and attacks that carbocation stemming from that resonance structure. You deprotonate it, and then this gives you the hemiacetal. Of course, this isn't overly stable, and so you can do the reverse chemistry to go all the way back down to the aldehyde or ketone product. Okay, so practice this, work at these mechanisms. I realize they're getting a little bit more tricky than the original SN1 and SN2 mechanisms, but I'm certain that if you keep on working hard at it, you'll master this material. Please don't hesitate to reach out to me if you have any questions. I hope you all have a blessed day.